Okay, I am here to talk about something I don't know enough about, but there is something I call the whiteboard effect, which is when you get a good colleague and you stand in front of a whiteboard and you explain something that's puzzling you, by the time you're done explaining, you probably understand much better what you were puzzled about. So this is, I ask your indulgence to attempt to use the whiteboard effect here to widen all of our understanding about data parallel programming. It's been important for a long time. Guy Steele and I worked for the same company decades ago on data parallel programming, and it's still a hot topic, and all the more now. This is me. I'm John Rose. You know me. I'm the JVM architect, I guess you could say. And this is what the lawyers want us to say. And it says that what I'm telling you is not to be trusted. And so don't take any of this to the bank, but I think it will be intellectually interesting anyway. So data parallel programming was born. Here is my take on what data parallel programming is, and I tried to sort of rederive the notion so that I would be at least halfway comfortable talking about it. I think the essential idea in data parallel programming is very simple. It's just the old idea of divide and conquer. It's if you have too much data to work on, why don't you figure out a way to break it in pieces and work the pieces in parallel, obviously. And that applies to inputs and outputs and temps, all sorts of data, and you sort of work on them concurrently. It does not make a commitment to how big those chunks are. But the important commitment is those chunks are processed independently. And therefore, because the data is partitioned according to some ad hoc rule which may be hidden from the user, the operations on all those chunks are the same. So that gives you this idea of one piece of code running across multiple chunks of data. I say about the same everywhere because there are lots of addenda and footnotes on this. There's lots of ways you can have operations be a little bit different, starting with divide by zero. But the nice thing about data parallel programming is it's not really that exotic. According to this definition, it'll run on any platform that will benefit from loop transforms, vectorization or unrolling or fork join. Anywhere that you can easily partition work, get the work done on multiple nodes and bring it back together, that's a good platform for data parallel. So it's kind of a nice fit to Java because Java is one of these I want to run everywhere type languages and runtimes. Of course, if you have special purpose single instruction multiple data hardware like the connection machine, then it'll run there too. Here is a running example I will be using. In classic Java, we're adding element-wise two arrays together. And this will look very familiar from any number of different languages. I want to call these elemental operations or element-wise operations because they do the classic data parallel thing of not talking to each other as they work in pairs, producing new answers into C. There's a very nice construct which actually turns out to be not so useful maybe, but it carries the point very well, which is the for all construct from Fortran 95, I think is the vintage of it. For all is a for loop, but in which the order of iteration is not guaranteed, and in fact the effects can happen concurrently, and so you're allowed to do all sorts of loop transforms on that without worrying about what order it should appear to the user. Most high-level languages that talk about arrays will give you some form of add two matrices together, add two vectors together, something like that. And so the only thing that varies there pretty much is how you write the assignment arrow. What else? Yes, and in JDK 8 you can do this too. In fact, this example was anticipated with small variations by by Vasanth and Eric's talk. But you take a range, and then you work over that index set. And those of you who are APL people are thinking iota right now. And you then take a lambda, which is not very APL-ish. Well, it could be. And you using that lambda, you pick out the two pieces you want and add them together. And then you'll notice there's no C here. C doesn't really appear as a side-affected target. It appears sort of all at once as the combined answer to the question. And that's actually an important property. Okay, so let's talk about hardware a little bit, which is a risky thing because I can say whatever I want because I don't know much about hardware. I rub shoulders with hardware people, but that not much rubs off. But let's suppose we have something that will run some instructions. It's listening to an instruction stream, which is what that little wavy lasso is supposed to convey. And it might be a Pentium, which is why it's got pentagons in it. I don't know, but it's some kind of a processing unit. And this is, I believe that when you're thinking about data parallel programming, you're thinking about sort of, on the one hand, streams of instruction going by, and on the other hand, there's some data which are arranged across some sort of orthogonal axis. And so two-dimensional pictures, I think, are useful for jogging our imagination. So this is maybe what it might look like when you add memory to the system and you have a full von Neumann system. And you see there are three variables stored in memory, and we are adding them together. And of course, those little pipes are how the processing unit somehow reaches in and gets information, peeks and pokes it in memory. The memory here so far is very old-fashioned. There's one port to it, and you can do one thing at a time, and there's just one central processing unit, and that central processing unit definitely is very central, and he feels like he's the top of the world. He's just he's got the title to the whole estate, and he's pumping all the oil there is to pump. By the way, that letter there is an actual letter Thorn, which is mispainted by sign painters everywhere as a Y. It's not really a Y, but that's why you get ye old. It really should say the old. That's the old memory, and it's old because, as I said, it's single ported. All right, so before I go a little bit farther, I want to say my working assumption for this talk, which I think is a reasonable one and defensible, is that data is not going to be single variables. We're not programming BASIC here. We're going to program APL or something like that. Data is found in arrays. Comes in big, fairly regular bundles. There's not a lot of loss of generality. The important thing, though, that I want to point out is that we have things that can be split in constant or log time. We don't have to work really hard, like chain down a linked list in order to do the subdivision trick that was sort of at the beginning of the thesis of this talk. Splitterators, by the way, are just a lovely way of expressing that. And you notice you don't need a splitterator on an array. If you consult the mug here, you will see you can have a splitterator that looks suspiciously like it's processing pasta. But that's an advanced business-only feature. So what are the key properties? As I said, subdivision is cheap. And then once you have the subdivisions, when you get down to actually doing the work, looping over the smaller chunks is cheap. Concurrent access is safe. And by concurrent access, I don't mean to the same chunk by different threads. I mean different threads to different chunks. That, again, is the thesis of data parallelism. You divide things and you conquer them separately. So independence of the iteration chunks is very important. So classic arrays in Java are okay, but there's problems with them. And I gave a talk about that last year, and the slides are posted, and we're working on it. Yes, I'll throw in some pot shots at arrays as we go along. So here is the previous thing with arrays. Now, I want you to think of the shading in those arrays as meaning that you're sort of pumping data in or out of these reservoirs of data. It's intended to remind you that things are flowing around. These are not static all or nothing chunks of data. These are data which are supposed to be streamed. You're iterating over them. There's some kind of a loop going on, and the loop is reading and write. The loop is reading one and writing, reading two and writing one. All right, moving forward. So let's go to Java, because this talks about Java as well. What does a Java VM think of when it is actually driving a CPU? Well, it's primarily thinking of, and this is my compiler centrism coming in, but it's primarily thinking of a stream of bytecode instructions. And then, of course, the bytecode instructions act on stack frames, and there's this whole rule about how they stack and what's in them and how you verify them. And one thing that's interesting about this is there's almost always, but not quite always, enough stack to get your job done. Sometimes, if you don't have tail call, things can go very badly wrong, as we saw with Guy's talk. But somehow there's enough stack. And in fact, there's a similar story with your shared memory. You of course have just DRAM chips somewhere, but Java virtualizes that with the help of the operating system and so forth to a big managed heap with lots of managed stuff. And the arrays here are sort of the almost right part about doing array-based data parallel programming. Again, there's enough of it to make the errors rare in practice of resource exhaustion. Most importantly, and this is something that we don't usually think of as Java programmers until we are forced to by bugs and race conditions, is there's a concurrency system, the Java memory model, which gives fairly precise guidance as to what's a race and what's safe. And maybe also what are benign races and what are virulent ones. So it provides ways to control against races and provides assurances that say you don't have to control all the time. For example, if you have beautifully coded final fields everywhere, then you can publish your data in your object by simply pasting a pointer, and there's no race condition that matters because the final variables are known to be settled before the thing becomes visible. Everybody knows about that, right? Final fields are really nice. This theme comes in later too. All right, so obviously the first thing you do is you make more threads, and then you have more concurrency, more parallelism, and everything goes fast and you're done. And so here's a picture of 3 threads doing completely different things, and in fact they're doing them in completely different places. So I've sort of twiddled the example so that it works, but of course it doesn't always work that way. But this is old school multi-threading, and we call it MIMD, multiple instruction, multiple data, which is like, what else would it be? But it's the opposite of SIMD, obviously. It's very general. It works okay if you jigger the example so that you're actually doing completely different things in your VM. But if you really want extra power and generality, then have them work on mutable data that sometimes is read across thread boundaries, and things get really powerful then. So MIMD code has to synchronize very carefully because the threads can be in pretty much in any state relative to each other. There's a wide variety, many degrees of freedom in interleaving, so you have to worry about all possible interleavings of effects. It's actually difficult to reason about, although if you have synchronization, that gives you some big hammers to work with. Another thing that's a side effect of having enough stack for all possible uses is that your thread actually has a big footprint. There's probably 10 megabytes at least of raw stack on it, and because you're spending that much space already, why not have a big rich thread object with lots of bells and whistles on it? Might as well. So there's things like thread local, which are really cool, and that sort of mitigate against making threads smaller again, which is kind of what we want to do moving forward, at least for GPUs. So here's an example of how things go wrong when you fail to isolate correctly, and so here's a race condition. Boom. A read before write possibility. So what went wrong? Well, every CPU thinks he's the CPU, where C means central. So there's a problem because they don't. You have to put them in a pretty heavy framework with lots of sinks and locks in order to make them cooperate properly. And in fact, the reality here is memory is central, not processors. obviously there was a racy input to CPU number 1 in the previous diagram. I would say, I'm going to just inject opinions at will here because this is my talk. I would say I think the best way to handle this stuff is to separate outputs and inputs and have them work at different times and with different visibilities, so that in fact if you're making an output, it probably should be a complete output that's freshly created and has settled data in it that then can be somehow frozen, kind of like a string body is frozen. You know nobody's ever going to change it and can be safe to share. You then pass it off to your consumers and let them read it. And if that's too much latency to get it all done, then you block it up. This is all about divide and conquer. So this is one reason that the value objects JEP includes not only frozen instances but also frozen arrays, so that you can safely create output values that can then be shared, and you can make proofs about the data being settled and not being tweaked accidentally while you're in the middle of reading it for the next phase of your calculation. Of course, there's also the double write problem. Again, it probably, this is my opinion, it would be best if output variables were written exactly once. And this is kind of like functional programming 0.1. But one way to do that is with stream.to array. And you saw that example in streams, where the final thing you did after making a stream that was adding up all your array elements was to create the new array that was to be the answer. And I would probably add a freeze operation at the end of that just to make sure no one would ever change the results. But logically speaking, you have a nice stream pipeline that ends up saying, okay, here's the answer. You've never seen this array before, so you never had a chance to put a race condition on it, and now you're just going to read it. So this is a safe idiom compared with first make a result and then do a bunch of multi-threaded stuff that's really okay, I promise, and then somehow all the answers are in that result. That's not a good way to program, in my opinion. Okay, so with race conditions, you can say, oh, Java model's broken, everything's bad, let's make new bytecodes. I think the bytecode semantics are not at fault here, and even the concurrency model. You can run Java bytecodes SIMD, and there are multiple proofs of existence for that. The managed heap and the safety and security especially are very helpful invariants, and I would strongly advise against breaking those invariants for performance sake or for GPU compatibility or something. And I'm really glad that the GPUs are sort of getting more like CPUs, so that we can do what's necessary to enforce the safety and security. And of course, all the Java programming things are right, including lambdas and streams now. Okay, so let's keep all that. What's a good notation for doing data parallel programming? Well, MIMD is, I would say, that sort of the basic root problem with MIMD is not that it's racy. That's a symptom. The basic root problem is that it says too much. It's too powerful of a notation for simple things like take some data sets and put them together and get new data sets. So, and in particular, the loops that you would write in classic Java for this, they promise sequencing, and it's really hard to prove, although Cliff has some good results here, it's really hard to prove that the sequencing can be dispensed with in the name of performance. The state of the art now is lots of annotation in your C loop in order to get the vectorizing compiler to offload it in the way you need to offload it for data parallel. It's not very satisfying. But for end users, simple notations are better, and in fact streams are a wonderful new compromise between simplicity and power, because you put them together like Legos and you can get, it's kind of like SQL queries or something. And then of course there's this reasonable thing of, well, if you add .parallel, then the system does its best not to disappoint you by making it slower, but will try to use more processing resources and make it faster. How many of you have ever been disappointed by the performance characteristics of the JVM? Moving on. Yeah. So disappointment is a possibility here. So it's not completely guaranteed, but that's the goal. The goal is to say, try harder to use more hardware on this data set, and that's what .parallel means. And so there's a great way to use data parallel techniques on that. And then the APL style or the MATLAB or R style bulk array operations are very user-friendly too. And in this room, maybe we don't use them a lot, but there is a very, as Jan said, there's an extremely deep user community for those things. And so maybe there's room for us to support this somehow in Java. For a quick win in this space, I just realized yesterday, Brian, maybe you already realized this, but default methods give a way of injecting methods into array types. Oh.
Yeah, that was one of those things that fell off the list of things to actually implement. It was on the wish list from the beginning, and it didn't make the cut. But
didn't make the cut.
The array classes require VM magic to.
Yeah, require VM. So that needs some prototyping and then some fooling around to find out what the right mix is that doesn't like break overloadings right now. Yeah, all that kind of stuff. But yeah, I'm kind of excited. I think we will actually. We're 2.5 steps closer to a VM and a language that has methods on arrays that make sense. That's good. Anyway. And then, of course, there's another user model or notation here which is very exotic, but sometimes it works really well, and there's been whole companies founded around it, which is a big array of pre-placed structs, all the same shape. And they amount to like slices. They amount to each element of that pre-placed struct across all the system is a stripe that acts like an array, but from the viewpoint of the compute model, the structs are operated on one at a time, but in parallel. So that's your classic data parallel as with the connection machine. Okay, and then a brief slide on timing, because notation is important, but you need to know when the things happen that you've notated. And so notation needs to explain sequencing. And data parallelism just says you have decomposed your data structure into some chunks and you're operating on them independently. But of course, if you're doing stuff with those chunks that actually reads and writes, and this is a streams issue too, and that's got some very fiddly language in the Java doc. What happens when your Lambda callback does a side effect or observes a side effect? It's tricky. It has to be clearly documented, and so there's some options. You can have a lockstep, or you can have little handshakes between totally local clocks, or you can like dispense with clocks altogether and have just sort of pure data flow with queues. This has been explored for a long time. I like the idea that's grown up in the GPU world of warps or thread swarms. It's cute because you take the familiar idea of a thread, which has a linear series of instructions that it executes, and then you put a whole bunch of them together to sort of saturate your CPU resources, and then as a proviso you say, well, they sort of execute at least within a group in lockstep or with the same instruction stream. Lockstep's really not the right idea because they might actually happen in multiple passes, and the HSA spec talks about this pretty clearly in an enjoyable way, at least for my taste. I think for most users, though, the best way to think about and to advertise the sequencing of effects in these data parallel notations is to have a framework that we'll call callbacks. And so the streams is an example of that. You give the lambdas, you promise to not to do anything untoward inside the lambda, and it will call the lambda whenever it darn well feels like in whatever thread, but hopefully at a useful place. And that's pre-existing in the fork join framework. It's the idea behind reactive frameworks or Grand Central Dispatch on this MacBook I'm running. So it's sort of a known good model. But let's, for the sake of drawing pictures, let's try lockstep again. The lockstep does not automatically remove race conditions, but at least cuts down on some of the degrees of freedom on them. So if you're going to race, you'll actually race more often, which maybe you'll catch a bug quicker. So here's a diagram, and this is like obvious, but I'm going somewhere with this. Now we have two CPUs that have partitioned, that have been offloaded with the two halves of the data set. So here's slice 0 and slice 1, and they're being operated upon. And you'll notice, if you follow the arrows, that the slices are totally independently processed, right? That's the whole advertised data parallel game. And therefore, there are no races, even though you might have very unpredictable writes into the two halves of C. That's fine. That's fine because you have a partitioning rule in it over the whole top of it. And it's a naturally simple tactic, which is one reason it's used a lot. So you get single instruction, multiple data. Let me put this here. You do the same thing everywhere. Now am I still, hold on. I need to do something here. Mic fell off. I think I'm audible still. With single instruction, multiple data, you can always look at it as a for-all loop. There's an outer loop that is going to tell that is going to operate on your loop body, and the loop body is going to run logically once per element, but at least once as a middle loop per chunk. And there may be side effects, and the effects will operate in an arbitrary order. And as I showed you with the diagram, it doesn't matter what order the effects settle as long as they're properly separated. And therefore, you can do all the loop transformations you like, and there might also be hardware efficiencies. I don't know what the big deal is about having one actual instruction fetch and multiple pipelines, but some people say it's good. So this seems to work. Let's add more GPUs, and we partition the data smaller and smaller, and what happens next? Well, you get to a place where you're suddenly experiencing physical limitations. This diagram is not just a cheesy attempt to suggest oil derricks, but it also has some basic validity because there's a sort of a dimensionality to memory that means it has more interior than it has boundary. And if you try to get to all points in the interior by replicating processors all along the boundary, those processors are going to step on each other. They might not make race conditions, but there'll be enough contention so that it'll be not a race condition, but a slow condition. That's a pun. So eventually you get dominated by communication. And so what do you do then? Well, you could throw away the notations and make notations in which communication is front and center, and so the user is punished for using communication by having to write a queue operation, right? I don't like that. In any case, it's not JVM-ish, I think. You could add placement to types. You could say, okay, we're going to pre-place your data near your processing elements, whatever that means. Maybe you have a NUMA system with memory associated with sockets. So we'll somehow expect somebody to place the data with the processing elements, and we'll make up the types match up, be the proof that everything is local where it needs to be. And one problem with this is if you're really seriously doing it with types, then I think you need like weird dependent types and all sorts of typefulness that's not in Java and won't be in Java anytime soon. So I mean, the closest I could get to this in Java would be like an inner class where you say outer or buffer thing, which is a locality dot new. It's not very flexible. You could add placement to objects, and that's probably more reasonable. Right now, people explicitly move their data with also an explicit reformat, and they call it marshalling. And it sounds like you're a field marshal and everybody's following your commands, but you're actually the sap that's waiting for things to move around, so you can get the push the button and press the compute. But the interesting thing about marshalling or moving is that it's a kind of a GC-ish kind of an operation. So this feels like something the JVM ought to help with, and maybe the hardware too. Was there a question?
John, depending on exactly what you mean by placement, it might actually be able to add that with type annotations and types. Depending on what exactly you mean by it.
Yeah. Well, I don't mean anything by it, because I haven't read. But you need to send me. You need to send me some information about that. Yeah. Thanks, Eric. Yes, I'm bluffing when I'm talking about placement types, but I know they exist in somebody's head. But here's my contention that comes out of this piece of the whiteboard drawing, and that is that the JVM should control copying. Copying not only of new space to old space, but from CPU space to GPU space. That feels like the right level of abstraction to be cutting things at. If we can give the JVM the right hints at the library level to say, okay, this stuff now we're operating on it over in this GPU compiled lambda. Maybe it's just a really cool HSA cache system that's unified across virtual memory, and the hardware caching stuff just goes to town and it always does the right thing because it's hardware, and we don't have to worry about it because we're software. But maybe it's as simple as a cache mechanism that just works out of the box, or maybe the JVM has to, like it does, with memory barriers and stuff, it has to do a little bit more work. Yes, William.
Curious if you can put sort of the duality of data copying versus operation copying. There's these two different ways. You got your data over here, but the other option is to send your operations over there.
Yeah.
And those are kind of dual.
Yes.
The database people have made a lot of leverage by doing the operation copying.
That is good advice. So William Cook is mentioning that you can move data, but you might also want to move the code nearer to the data, which is, of course, a distributed computing play if you have a very big cluster with segmented big data. Yeah, that might be the right way to do it. It depends. That would lead you to a clustered JVM or a JVM with these big dissimilar chunks, a very non-uniform memory. So that's we have to evolve a little bit before we can make memory that non-uniform, but that might be the right answer.
This is actually a third tactic. It's basically moving both the data and the code to a new place where it can be more efficiently computed, right? So you can end up in a situation where you're moving both the code and the data.
That's what a GPU does, in a sense.
Yes, moving both code and data is what the GPU does. Yes, and that's.
The point is that we're not in a world where we can uniformly think about moving whatever chunk we need to move around to the place it needs to be, either code or data. Right now, it's like, well, we think the data moves around pretty easily, but code doesn't, and we don't have the abstractions to make this easily make sense.
Well, what if we had a format for code that was the same everywhere with the same semantics, but it could be compiled differently in the different locales? Yeah, Dane.
I saw a presentation where they were talking about pushing code down into the flash chip and getting unbelievable performance because you move a huge segment of the memory by applying, these were data guys, applying where clauses in the chips and only moving up the segments that match, and it was unbelievable.
Yes. Oh yeah, if you can actually put processing into the DRAM where there's some, you realize there's a CPU that you never noticed, or a programmable gateway or something. That
you notice that the memory is actually a database?
Yeah, the memory is a database.
Some smart things with your data before it sends it out at you?
This is just for higher-end flash controllers, and it's awesome.
Let me do a time check. We started a little late, but
Yeah, we started a little
not that late.
And we're coming into the workshop / lunch, so you can go over.
I'm going to go over slightly, but not much. Okay. So here is forthwith the striping idea drawn out in living color. And of course here we pretend that there's some way to place the relevant piece of data, the relevant segment, next to a processing element that has a nice clean port to that memory, but not necessarily to other memory. So that's good. That was the thesis of the connection machine, and that's why you get some languages that talk about very widely spread arrays of little structs. And so if you cut vertically through this granite rock here, this oil-bearing shale or whatever it is, if you cut vertically, you'll get a little struct with 3 different elements in it. no matter where you cut. And that's from the point of view of that one little struct, he's the central processing unit, and he's centrally processing C equals A plus B. And this localizes the traffic at the expense, of course, of forcing your data to have to spread out in a funny way. So what to do about that? Well, how do we make it happen? Well, we could use malloc and free, right? And we can have total control over our marshalling. We can just be marshals all day long. And of course, JVM programmers don't really want to stand for that, Java programmers, because there are too many ways to make mistakes and crash your system. Also, and this is maybe less obvious, if you have manual copying and you're not relying on the memory fabric to do your copying or some low-level agent to do the copying, you probably aren't as smart as the low-level agent about things like pre-positioning or prefetching or predicting streams of fetching. And remember, part of the thesis here that I've claimed is that we're doing fairly regular traversals through arrays. Now, you can do software caching, right? But it's a nightmare. It's better. This is one of those things where I say, hardware people, please take care of this for me so I can forget about it again. What happens when this works well is that the hardware is working in the memory fabric is working in parallel with the processing elements to deliver the needed data just in time, or to flush out the written data just in time to make room for the next chunk of written data. And of course, it never works exactly perfectly, but there's a lot of effort put into overlapping the latencies of the memory reads and writes, which if you naively write this using malloc and free, you lose all the overlapping latencies. All right, so or maybe the JVM does. Do we have JVMs that do manual cache management? I hope not, but it could exist on a very low-level hostile system. But it's really the thing that I like most about HSA is the unified. Well, that's the thing most about HSA is the unified address space, and that gives a chance for this prefetching and latency-hidden memory traffic to happen, and to save a lot of the embarrassment that comes when you marshal your data and you've been marshaling. Then it happens quickly that you get your answer, and then you marshal it back and you realize it would have been faster just to run the whole thing on a Haswell with the regular memory. Yeah. So, what are the answers? By the way, imagine for a moment, imagine a world where you don't have the memory fabric and you have to do everything manually. You will have to learn about things like read to share and read to own, which are two distinct ways of using that formerly uniform von Neumann memory. And read to share and read to own actually correspond to up-level, interesting life cycles of Java objects that ought to exist. Read to share means I'm reading a value object or a frozen array, something that will never change and that I can replicate with impunity. Read to own means I need to poke this thing for a while, and I would really like to know that I'm the only thread poking it. I would like a hardware signal to invalidate. No, sorry, not hardware. I would like a software check to say that no other thread is side effecting this thing or even reading it until I'm done writing it, right? So these concepts are worth thinking about because they do up-level into meaningful APIs. But that doesn't work with Java arrays. So until we do new Java arrays, we're going to be a little bit stuck. But they could have new arrays could have these new safety rules, not just bounds checking, but thread ownership checking, and safe partitioning and so forth. So a little bit more. What's in a Java GPU thread? Well, it's not going to be a subclass of thread, and there's just too much system stack for starters. Minimally, it's what the for-all loop executes in one iteration. So what's that? Well, that's a piece of code, a stream of bytecodes. That's good. And it's an iteration variable instance. Well, that's interesting. So your thread could be a 32-bit int. That's pretty cool. In any case, your GPU work item has to know what his task ID is. And that sounds familiar too. The GPU thread also could maximally be the whole loop, some other decomposed in some other ways. And in fact, Java streams, as I've said it before, can decompose in interesting ways. Somehow, the thread emergently has to be, maybe after fork join and work stealing has decided how big the chunks are, maybe there's a low-level thread that says, well, I'm gonna run my way through a segment of the iteration space as if a bunch of elemental threads came into being and died once per iteration. But since you don't observe them, it vectorizes away. All right. In any case, I think there is a natural question. If I'm running GPU code, what does thread.currents mean? And I think we have to answer that squarely. And part of the intellectual exercise of doing this is to say, well, what would a GPU thread be if we were able to forget that there was a Java thread present? And this will actually take us into reactive programming and callbacks that don't execute inside threads also. So, and then of course, if you've got a mesh, a multidimensional mesh, then your thread ID is, as in HSA, it's a tuple of index values. All right, there's some more meditations on very idiosyncratic ones on what thread swarms and warps are like from a JVM-ish point of view on this referenced wiki link. And we're almost done. Where am I with this? Yes, there's an example of maybe sort of a minimum thread swarm. It's a piece of code with a hole in it. And the code of the warp is where that hash sign is, and the thing around it is the sort of the family of the warp, and the X value is the individual instance of the family. So that's one way of looking at what a thread warp might be from a Java point of view. And so this actually works. You can pretend. Virtualization is great. Somebody said, I think Peter Deutsch, cheat all you want as long as you don't get caught. You can pretend that there's a million of these tiny little things as long as you don't reify them and observe them too often. And so here's a bunch of these little GPU-ish things, and let's say we've arranged memory properly so that the communication overheads are dealt with somehow, and they just keep multiplying, and maybe there's just who knows how many of them, but they're not real. So don't try and build this for real. Well, actually, it has been tried, and the results are interesting. But virtualization is a safe bet. So one more issue that I want to point out before I close, and that is alignment is important, and not in the sense of mod 8 or mod 16 or something. When you have, say, A and B adding together, it doesn't work to have A sub 10 way over here and B sub 10 here. A sub 10 and B sub 10 have to be eventually in the same place at the same time so they can be put into registers and so forth. So a memory fabric does that for you beautifully, so beautifully that you sometimes forget that it's being done until it misbehaves and then you realize that it was being done. But somehow those two arrays need to be aligned, and given the fact that you're doing this data parallel bulk processing, why not arrange the alignment beforehand in such a way that the cache fabric doesn't have to make a separate decision for every cache block? That would be nice. So maybe there's some way to hint the memory fabric that these parallel ranges of memory somehow need to go together. I don't know what that looks like, but if the VM is managing marshalling explicitly under the covers, then clearly it has to think about these things. And this relates, by the way, to up-leveling to the higher level idea of shape conformance, which you'll see in APL and other array processing languages. And there's a really interesting take on it. Gary Sabbatt's dissertation, he introduced this neologism, parallelation, which is a parallel relation. And it's a way of thinking about this particular problem of aligning parallel data. So how do streams deal with it? Well, with IOTA, with a stream of indexes, as we saw before. And that's quite workable. It does seem backwards to use this enormous stream just to produce some ints, but it does work out. I think there may be a principle here. Let me suggest that if you're working with if you're working with element-wise references to data parallel data, then in a JVM-like world, whatever it means to say Q sub I, A sub I, B sub I, that better be something that you can pick up and move and his neighbors with him. So this idea of moving can't be just delegated to the memory fabric. Even in the best of hardware, it ought to be something that the JVM can help move with a continual alignment to the processors, or move the processors closer to the memory where it stands, of course. I'm assuming elemental ops. None of what I've said previously matters if you extend it slightly to include stencils, nearest neighbor communication. So this little, adding the little purple arrows is fine. It doesn't kill you or with over extensive communication. You can even do log-n tree spanning trees. You can do individual heap accesses or table lookups if your hardware allows. And by the way, in passing, GPUs need to allow all sorts of things, a full Java model, or else your bytecodes will have different semantics depending on whether you were offloaded or not, and that's not acceptable in the Java world. So we do have some of these log-n algorithms too in JDK 8, such as parallel prefix and the wonderful collector reduce mechanism for streams. It works out of the box, including user-defined reduction operations. Segmented parallel prefix does not yet have user-defined operations, but eventually we might get there. It requires marination and thinking. That reminds me we're going to the fault line tonight. And so, but I have a dream that the grouping by operation doesn't necessarily mean a hash map or a tree map, that it means a segmented scannable data set. Okay, one more thing, really one more thing, is this relates to vectorization only in a sort of tangential way, although you might think, well, how do vectors play in this, right? Because you're talking about arrays, so vectors are arrays. Really, the vectors are an important component of getting another 2x, 2.5x speed up out of your loop transformed loops. And there are some libraries that do data parallel operations specifically in a way that can be built up out of vectorized loops. And I kind of admire the CVL library, which is Guy Blalock's work, which he built Nestle on top of. So but this does beg the question, does Java need a vector type? And we can argue about this, but if it does, this is clearly a use case for those pesky 128-bit types that we've been talking about all today and yesterday. Java's challenges I've gone into, but here's the short list. I haven't talked about reference identity, but you can sort of get what I mean. If complex number is the same as another complex number, but their reference is different, how do you store that information? Oops, you shouldn't. So what do we have in Java that we can continue to use? A good memory model. The final variables are great. Eventually we'll have value types. And of course, all the kinds of encapsulation we can eat. Plus, good streams out of the box. And what did I skip? Yeah.
So how do you cope with the semantic mismatch when the GPU doesn't support the semantics of Java?
The question is, how does one cope with the semantic mismatch when the GPU just refuses to do things the Java way? And an example of that might be to return a nan instead of throwing a div0 exception. Would that be is that the sort of thing you're thinking of to start with?
Sure.
Yeah. Well, I think as I alluded to earlier, if your code does different things unpredictably depending on the mode under which it was compiled, then you're not in Java anymore. So it comes back to how do we get the GPUs to deal with these corner cases? And Java is Java's kind of weird because it has all these under-exercised corner cases. There's a null pointer exception about to jump out at you from half the bytecodes. That's an exaggeration. but it doesn't actually jump out because your code is correct enough. And when it does jump out at you, you realize you've got a bug and you fix it, or you re-examine your assumptions about the system. If the GPU didn't also throw null pointer exceptions or array store exceptions or range check exceptions or div 0 exceptions or so forth, then you would be losing an important value proposition. The saving grace about this is what I said about it hardly ever happening except when there's a bug. So you can, it is reasonable to say, and we do this in compiled code now, we've been doing it for 10 years in Hotspot, it's reasonable to say, I'm going to assume that this corner case will never happen until proven otherwise. I'm going to put in the necessary back-off logic, and if somebody does do a div 0, I'm going to detect it, and then I'm going to take more care about that in the future. But I'm not going to sacrifice even one div 0 event for performance. So that means the GPUs run slower. This is like the fuse multiply add question. We can't run our Pentium chips at full speed unless Java will emit fuse multiply add. Well, under what circumstances would you like it to emit it? Well, I just want to say, A equals B plus equals B times C. Well, that's not standard Java to use fuse multiply add for that. That is a multiply followed by an add. Oh, well, can you give it to me anyway? No, Java is a standard and it has to work kind of the same everywhere. That's part of the deal. And likewise with GPUs, we're going to go through that pain too.